How you doing? This is the third session of chapter 2 of Fluid Mechanics 1. I hope you are doing well. And we are going to illustrate the pressure variation in a fluid at a rest. Follow me with the whole video. As I told you, the subject of this session is pressure variation in a fluid at rest. My name is Amir Raza Talaqat and my email address is amirrazatalaqat@gmail.com. I'll be so much delighted to answer all of your emails. It might take several minutes to several days, but I try to take an action as soon as possible to give you the answers you are looking after. So there are some principles in this section, which is section 2.3. As you know from the previous session, we had the equation 2.2, which was regarding the pressure gradient, which was gradient of pressure minus gamma k is equal to rho A. The term of rho A is going to be 0. The main reason to that is we are considering a rigid body, which is having no acceleration. So the only term we are going to consider for the pressure gradient is in the z direction, because the two other are 0. Since we are only depending on the density, we are going to have this equation here, which is delta P over delta Z equal to minus gamma. As long as it is illustrated in a single direction, we're going to define it as normal deviation, which is dP over dZ equal to minus gamma. This equation means that we are having a constant, but the constant term is only regarded for specific weight. How we can identify the fluids which are having a specific weight? The answer is for the fluids we already have a normal specific and a constant specific weight. They might vary due to elevation, but the variation is negligible. Or some other gases like air or any kind of aroma or any other kinds of gases. But we have to stipulate the equation 2.4 in order to verify the usage of a constant specific weight. Here it is. As you know, the specific weight is the multiplication of density multiplied by gravity acceleration, which is g. In engineering, the g gravity acceleration is always constant. So this means that we have to look after the consistency of density. If we have a fluid like liquids which are having constant density, they are regarded as incompressible fluids as long as they're having constant density. The variation is density is somehow negligible in over large vertical destinations. But for gases, we might have to be looking after specific gases. But for liquids, we are okay to have integration. Doing the integration, we have in here from P1 to P2, integral of P1 to P2 for dP is equal to minus constant specific weight, integral of z1 to z2 for dz. Doing the calculation, we have this equation as equation 2.5. Having it in a normal order, we are having equation 2.6 and 2.7. The ultimate equation is 2.7, which is regarded as a hydrostatic distribution, which is P1 is equal to gamma H plus P2. The hydrostatic distribution has some details I'm going to illustrate in further. One of them is here. As long as we have a hydrostatic distribution, the pressure gradient in a vertical direction only depends on a specific weight at that point. Another thing is that as long as we have a constant specific weight, this means that we have a constant density, which means we are considering incompressible fluid at rest. The term H means hold up distance. It is interpreted as the distance, the height of the volume of the fluid of having a specific required to give a pressure difference. So the H here is hold up and distance, which is pressure head. Let me repeat it again. Pressure head is the height of a column for fluid of a specific weight required to give a pressure difference. To put it in a nutshell, pressure head is the height we require to maintain the pressure difference of the fluid. In this slide, the main point is that we have to know the reference pressure. You see in this picture, we have a PA 10 pounds here and 0 here. The 0 is owing to the fact that we are considering this section as a reference. So the pressure at reference is 0, which is P0. Usually it is atmospheric pressure. So if we have this picture, the pressure head is 23.1 feet. And the P at the end is 10 pounds because it is exerting 10 pounds as a weight. The whole pressure is going to be equal to gamma H plus P0. P0 is the reference. Gamma H is the specific constant and specific weight of fluid, and the H is the pressure head, 23.1. Just remember that if you're dealing with this equation, you have to consider is homogeneity, which means the units has to be homogeneous in both sides, and you must have incompressible fluid at rest, because as long as I've told you so many times in previous sessions, if you not regard the assumption of no shear stress, this means you might not have constant density as well as you might not have ability to use this equation. Excuse me. So the other point of equation 2.8 is that as long as you have the height, the specific weight, and the reference pressure, it is not important to verify the shape or the size. The example is here. Take a look at this figure. We have three different shapes in three different sizes. As long as we have same specific weight, same height, and the same reference pressure here, here, it is not important to regard the shape as well as the size. So here we go for the first example of this chapter, which is due to the pressure-depth relationships. Follow me with the solving of the example. So guys, here we have a solving problem of example 2.1 from chapter 2, section 2.3, which is regarding pressure depth relationship. Let me identify the question for you. Because of a leak in a buried gasoline storage tank, water has seeped into the depth shown in figure E2.1. The specific gravity of gasoline is SG 0.68. So, specific gravity of gasoline is 0.68. The question wants us to determine pressure at the gasoline-water interface and at the bottom of the tank, expressing the pressure in units of pound per square feet as well as pound per square inch, and as a pressure head in feet of water. So, as you know from previous equation in this section, we have P is equal to gamma H plus P0. If we want to have P1 is equal to Sg multiplied by gamma H2 H plus P0, which we have 0.68 multiplied by 62.4 pound per cubic feet multiplied by 15 as a height of gasoline, 15 feet, 17 feet, plus P0. This means that we have P1 as 721 plus P0 as pound per square feet. So, if we have a P0 as 0, we have it already. Since we are regarding this 0, we are having it already as pound per square feet. But if we want to convert it to PSI, we shall have this. PI is equal to 721 divided by 144 square inch over square feet, having this unit. In order to convert it, we have to divide it by 144 square inch per square feet, which means 5.001 pound per square inches. If we want to have the height of a pressure 1, the pressure head of 1, H1 is equal to P1 divided by gamma H2, which is 11.6 feet. If we have this as 721 and this as 62.4, both in pound per square feet. And this is the cubic feet, excuse me. It is pound per square feet. Let me tidy it up. Yeah. So, if we want to have the pressure of 0.2, this means that there is a pressure 1 at the over of that point. This means we have this as P2 is equal to gamma H2O H2O plus P1. 62.4, I'm not giving the units again, just substituted in the equation, multiplied by 3 plus 721, which means 908 pound per square feet. Dividing it by 144, we're going to have it as pound per square inch, which is 631 pound per square inch. In order to have its H, the pressure head of 0.2 is P2 divided by gamma H2, which is 908 divided by gamma H2, which is 62.4, which is 14.6 feet. H1, yeah, here, pound per square inch, here, and here. Welcome back, guys. There is one more point that I need to look after. You have to look after the equality of pressure at equal elevations for hydraulic jacks, lifts, as well as the hydraulic controls on the aircraft or other types of heavy machines. The concept is illustrated in this figure. You see, as long as you have the same pressure at both of these sections, P2 is equal to P1. This means that F1 over A1 is equal to F2 over A2. If we want to verify the F2, we have to multiply F1 over A1 to A2, which is here. If we do that, we can gain the forces. This is the relation between the forces as long as the pressure at both sections is the same. So guys, this is the end of this session of chapter 2. I hope you have acknowledged the subjects very well. I'm very happy to have you till this moment of video, and I'll be so much appreciated in order to subscribe the channel in order to get the notifications of upcoming videos. I bid you all farewell. See you in the next sessions.